Hi, this is the lesson for Chapter 1, Introduction to Dimensioning and Tolerancing. Let's take a look at our objectives. Okay, the first one is explain the importance of specifying dimensions and tolerances in compliance with applicable standards. Second one is recall the history and development of dimensioning and tolerancing methods. Number 3, explain how teamwork can result in better definitions of the dimensions and tolerances in the design process. Number 4 is recall the job titles of those who can assist on the design process team. Number 5, recall the dimensioning and tolerancing skills needed for success in design or production-related occupations. Number 6, understand the relationship between 2D orthographic views and how they are created using orthographic projection. And number 7, there's a seventh objective. That's listing the terms. So see your objective sheet. You should have it right in front of you right now while you're studying this to go over this material. Okay, standards provide clarity. Okay, so tolerances are an acceptable dimension variations that are permitted on a feature. So tolerances will enable achieving the best product at the lowest cost, and tolerances must be correctly calculated, applied, and interpreted. Correctly applied tolerances result in fabrication of the intended design. What all of this means is nowadays there's a lot of manufacture of mechanical components and assemblies. And what we use the tolerances for and GD&T for is to precisely define what these parts are and how they fit. So that's why we keep saying tolerances must be correctly calculated, applied, and interpreted. So you need to know how to dimension parts, you need to understand mechanical drawings, and you need to know how to apply tolerances. And to apply tolerances correctly, you have to have some understanding of manufacturing processes, because what we do in mechanical parts and assemblies nowadays is all parts are interchangeable. You know, we make assemblies with interchangeable parts. So we define the parts on drawings and we send those drawings out and manufacture the parts to the drawing, knowing that if we've done our work properly in terms of defining the tolerances and defining all the parts properly, that once we get this basket of parts together, we will put them together and they will function as intended at the next level assembly. Whatever that next level assembly it is, it could be an aircraft, it could be anything, mechanical clock, anything at all. So tolerances need to be understood and applied correctly. So what happens if we don't apply tolerances correctly? Let's say we put too tight of tolerances on everything. Okay, what's going to happen there is that directly affects your manufacturing costs. So you can limit the number of potential suppliers, because in some cases, some suppliers may not have their machinery to hold those tight tolerances, or they might not have the processing capabilities to do so. So you can err on making your tolerances too small. And you can also err making the tolerances too big, okay, because the parts may not fit in the assembly. They might be loose, they might be sloppy, not function well together, they might have excess wear. The assembly function might be negatively impacted, and customer dissatisfaction, and you could have increased returns and it costs more. All in all, having the wrong tolerances, either too small or too large, can cause lots of problems and generally just be bad for business. Too small, they're driving up costs. Too large, then you're probably driving away customers. So there's been a lot of developments in product documentation, establishment of distance measurements. I think we're talking about the second objective now. Recall the history and development of dimensioning and tolerancing methods. Establishment of distance measuring. So we got the U.S. customary system. We use inches, and the SI system, the metric system, uses the meters. So typically for mechanical drawings, we're talking about inches or millimeters that are the typical. So establishments of dimensioning and tolerance standards were just very important, to develop these, systems of units. And computers and computer-aided designs have really helped that too. Now, It for GD&T, it doesn't matter what units you can use. You can use inches or millimeters. It's both are equally acceptable, but the unit of measurement has no effect on the dimension application. So it does actual, all the changes is the actual numerical value and the dimensions and how the decimal values are shown. We're going to talk about that in a minute. Dimensions are expressed in either inches or millimeters, and what we need to do is to state that clearly on the drawing. We typically do that with a note on the drawing to prevent confusion. You'll have a note on the drawing that says all dimensions are in inches, or alternately, all dimensions are in millimeters. How did we get here? We had to develop a standard for dimensions. If you look back in history, a lot of ancient societies were very successful building parts. The Greeks and the Romans, obviously. So they had developed their own systems of units, so they could be as successful as they were as the builders and constructors that they were. So that's where we get these, different units called cubits, spans, palms, and digits. These have all been used over 5,000 years. So based on defining features present in nature, so a palm, for instance, was the width of a palm, for instance. So the royal cubit was used by the Egyptians, and that was made of some black granite, and it was based on the length of the pharaoh's arm. Reference against which measuring sticks were calibrated. So all the architects would go out; they would have calibrated measuring sticks, and they could use those to determine if they were making everything to the proper sizes. And then we ended up with the meters here, standard meters in 1799. That was when it first started. So 1/10,000,000th of the distance from the North Pole to the equator measured along a longitudinal. So here what they're using is actually using physical measurements on Earth that they could come back to and calibrate back to. And then that developed into the standard meter in 1960. And then finally we got the standard meter in 1977. That's the distance traveled by light in a vacuum um, in in a certain time period. And then the other thing we needed to develop is measuring tools, precise measuring tools. What you see here is a scale and a caliper and a dial caliper for measuring. And of course there's micrometers, height gauges, and all kinds of other measuring equipment that we use nowadays to verify that our parts are good. And eventually we developed documentations and standards. Dimensioning and tolerancing standards were developed by the ASME, the American Society of Mechanical Engineers. Tolerance is smaller than accuracy of distance measurements. Standards are really not appropriate. I mean, if you can't, measure something down to the if you're incapable of measuring something to the tolerances that you're specifying, then it's really not any good. And then accurate distance measurement standards are essential to specify and achieve accurate dimensional results. So if you look at this drill bushing here, I mean, this is 5/10. This is a 1 inch diameter with a plus 5/10 tolerance. That's 0.0005. I call that 5/10. If it was 0.005, I would call that 5/1000. But this is plus 5 minus 1. This is a very tight specification, and you would have two things. You need to be able to measure that, and you need to have these tolerances defined to a standard before you can even begin to conceive of creating a drill bushing that's dimensioned like this. Okay, so standards provide terminology, symbols, and other methods to define and communicate tolerances. They allow for a single interpretation of requirements, and then applicable standards must be known. So when you're defining a product, and it's got to be based on a previous standard, that standard must be used to determine the applicable requirements. So you apply the standard when you create the drawing, and you apply the standard when you interpret the drawing. Tolerances. Machine quality, among other factors, affect feature variation. It is essential to define the amount of acceptable variation, and tolerances specify acceptable dimensional variations permitted on the feature. And you should only specify degree of dimensional accuracy necessary for the parts to assemble and function properly. Yeah, you don't really need to take things to, 5 decimal places unless it's absolutely required. I'm going to end this movie right here and pick it up on the next movie.